Good morning, sir. Myself Chaitanya. I am currently pursuing my BTech in SY Artificial Intelligence and Data Science, and I am from Group 17. So I have selected a topic regarding the self-driving car, a real-world application. So the collision avoidance and the navigation, how it navigates to the area on the road with the help of the semantic segmentation. So everything I would be explaining in the code. So at the starting, I have divided my project into the three modules. First one is perception software, the second one is planning software, and the third one is control software. In the perception software, I have implemented YOLO and MiDaS, as well as I have implemented the byte track. So YOLO is nothing but for the object detection and their class and their so for the representation of the object in the frame. So MiDaS is nothing but depth calculation, the distance between a object which we are driving a car to an opposing vehicle. And in the tracking, so normally I have implemented byte track. So, and also I have implemented DeepSORT. So I have compiled the DeepSORT as well as the bytrack. It's the perception software, and the output of the perception software is being sent to the planning software. In the planning software, I have implemented the semantic segmentation. So to find the drivable area on the road, and I have implemented the Gestalt algorithm for finding the best path. So we would be getting the instructions like move right or move left. So you can overtake the vehicle which is before, and the output of the module 1 plus module 2 is being sent into the module 3. In the module 3, it's an control software. In this control software, we would be getting the steering angle and the brake or the acceleration and everything low level commands are being getting in the control software. So basically, I have taken a real world video and converted into the frames. Then after compressing decoding, I have preprocessed and implemented the model on each and every frame and at last compressed it and stacked that images into the output video. So everything I would be showing in the code as well as the output videos. And at the starting, I have installed the dependencies of our project. So Alterytics and everything for the YOLO and Note. I'm especially using version 8 YOLO for the small and it's fast and also it's easy to use, right? So here I have imported my dependencies. So for uploading the files from my OS to the Colab environment, I have used from Google Colab import files, and I have imported YOLO as well as I have imported my operating system for the uploading of the files. And I have divided it. I have denoted two variables or declared two variables input video path and the output video path. So I have kept a random name with the same extension as the video which is in my OS. So in this code, I would be changing the name of the input video path or with the same extension. Everything is done in this code. So at starting, I have uploaded the video from my OS to the Colab environment with the help of the files.upload. And in the upload, I would be getting the path of the file in the Colab environment. So, and uploaded file name, a variable I have inserted to none. So with the help of the if and elif, I am finding that if the input video path is been similar to the uploaded video path. So if both are same, I would be allocating the input video path to the uploaded file path and everything. It's the same logic for changing the file paths to print whether the file is being loaded or file is being not loaded. And from here, our module 1 starts. So I have already told you that there are totally 3 modules. In the module 1, so the first one I'm doing is detecting an object and the class of the object in a image frame. So first one I have imported, I have created, I have initiated a YOLO model, and by default .mp4 and every video are in the compressed state, right? So for the pre-processing and the processing or for the applying the model on that particular frame, we need to be getting the raw data or the raw RGB numpy array. So with the help of the video capture, I am decoding that compressed into the RBG numpy array. So if the cap is nothing but the numpy array of the frame, right? If it's not opened, so I would be printing that so couldn't open that video on that particular path else. So here I am calculating the width, height, and the FPS and frame width and everything of that particular input frame, because the output video frame should be also with the same parameters and with these same attributes, right? So I am calculating this at the first and at last. I have created a container out. In that out, I have stacked the output images frames, and that output images frame should be same as this input features. So I would be explaining that too in the next code. And I am using the MP4V as a codec because I have compressed, I have decompressed the video for the analysis purpose, right? Again, for the visualization or for the downloading and visualization purposes, we need to be again the compressing of the videos. So with the help of the codec, I am creating a variable, the container out, the same parameters are the same size, the FPS and everything, and also the compressed version as the same input image. And from here, I would be calculating the number of frames and applying the YOLO on that particular frame. So while we remember cap is nothing but the RBG numpy array. So I am storing my RBG numpy in the frame, and the RET is nothing but it's a boolean, true or false. So it basically tells that end of the video or not. If RET is a false, so it's basically the end of the video. And for each and every numpy RBG numpy array, I am applying this YOLO V8, right? And in the results, I would be getting the classes and the confidence interval and the boxes which is mapped around the object or the vehicle in the image. So what I'll do now is for the visualization purpose, I will plot this object in the results for the visualization. So I will be using the for loop. You can see here. So for I in results, and I have denoted a variable a frame which is after a pre-processing frame. So in that frame, for each and every that particular frame, so I am storing that market frame. So I am replacing or I am storing that market frame. And that last out dot write is nothing but this out is an object which we have created with the same attributes as a input video with the compressed version, right? So the images would be stacked in the compressed manner. So at last we will be getting the full video, um, same length as the input and input video and with the same parameters and everything, but with the YOLO. So this part is nothing but for the printing purposes, how many frames are being processed and everything. And at last I am releasing everything. So it's the code for the YOLO. So I would be showing a simple architecture as well as the output of the YOLO. So you can see here it's an workflow of the YOLO. I have already told you that we would be sharing the compressed video file. Then a raw frame numpy is being stored in a cap, and we are applying that YOLO. So we'll be getting that boxes, and we are again compressing that stacked images. So these are the total flow of the YOLO. And after implementing the YOLO, the output video would be something like this. So basically, it's the input video I have given. So you can see the input video. So it's an real world data, the real world video. So after applying the YOLO, I would be getting this with the confidence interval as well as in the final module 3, I would be removing this person and everything in the car because I am adjusting the frame size for the extra algorithm. So it's an output after passing into the YOLO. So now this video is being passed as an input to the MiDaS, or the first video or the input video which we have passed the YOLO can also be sent into the MiDaS, and implementing both MiDaS plus YOLO for the depth as well as the recognition of the objects. So it's the same. So I have passed the first video, input video into the second YOLO plus MiDaS for the visualization and for to understand easily. So first I have its same code, and first I have imported the V8, and I have got the parameters of the input video, and I have defined the codec, and I have retrieved the each and every numpy RBG numpy. So and I have so it's an first code, and now we are going to the YOLO plus MiDaS. So I have imported my dependencies, and so I am using GPU so for the parallel execution. CUDA, and it's the same code. At last, so I have defined the paths and the YOLO model, and also these are the I am loading the MiDaS depth estimation model. So the model that MiDaS gets the processing or the finding depth of that particular image, and processor MiDaS which process the image and which is been sent into the model MiDaS for finding the depth. So I am defining the parameters and initializing the models in this particular section of code, and so I am retrieving into the raw data from the compressed video file. So it's same as the YOLO code, getting that parameters and codec and getting the frames. So in these frames, first I am converting these frames. So BGR to the RBG because OpenCV would be retrieving the numpy in BGR, but in the MiDaS we would be needing the in the form of the RBG. So I have converted to BGR to RGB. Then so this input are nothing but the stack of images which have been processed. Now we need to be finding the depth of this input. So I have applied the model.midas for which I have denoted that before. So and this inputs it's same as in the above variable is being passed as a parameter. So we would be getting the depth or the distance between the present vehicle which we are driving to the before wake up, and I am resizing the image as the original images. So because the output and the input both should be in the colliding manner, right? So I have converted the depth maps and into the numpy for the normalization purpose, and everything has been done in this section of the code. And after that, I have imported the model which I have run in the first cell, and I have done the fusion of the both. You can see here. So I'm taking every copy and I am applying that boxes and I am mapping that. So you can know that class ID and the class name. So the for the every class ID, we are mapping a name, it's and class name. So class names are nothing but the car, truck, bus, and the person on the stop sense, everything. And also I'm finding the depth or the distance between the our vehicle and the vehicle which are moving in the road. So you can see here it's the formula and it's an inverse, right? So we are calculating depth equal to 1 by depth map of the numpy because while doing the MiDaS, we would be getting the inverse value. So we are dividing by 1 and we are drawing the rectangle of that unaltered frames and everything. And we are keeping a label on that each and every frame as well as, and we are writing that each and every processor frames into the compressed man.mp4. So stacking of this as an output image. And at last, we are releasing everything. So it's the YOLO plus MiDaS architecture, which 1+2 architecture, and the output would be getting. So this is the total idea of the architecture. We would be passing the compressed input and converting into the raw frame on the YOLO detection MiDaS. And tracking, I have used especially byte track. So in the next section of the code, we would be discussing about the byte track. And I have compared the byte track with that the algorithm for the tracking of the vehicles. I mean tracking of the vehicle, etc. So I would be showing that section of the code and everything in the next cell. And this is the video with the YOLO and with the depth. So you can see that the car is it's giving the depth is nothing but distance between the present and the vehicles which are moving front. So you can see the output of the YOLO plus MiDaS. So we can yeah we can move to the cell 3. It's nothing but applying the byte track. So I am downloading the dependencies and then I am importing the the which we are needed for our project, and I am enabling my CUDA for doing the parallelism. So I have loaded my YOLO model as well as the depth estimation model. So here I have initialized the tracker. So for to track the object or to track the vehicle going in front of us. So I have initialized it to the byte tracker. You can see here. So tracker trap equal to byte tracker and byte tracker and device equal to device half equal to true. So if the tracker is not initialized, it would be printing that tracker is not initialized failed. And if it's initialized, it would be printing that it's successful. And you can see, so the tracker is being initialized successfully in the output. So it's YOLO plus MiDaS plus the tracker, right? So I have imported everything. And so I am opening the RBG numpy and again, so I am getting the parameters or the attributes of the input video. Then again, I would be calculating the codec. And again, I am training the numpy of each and every frames, which is stored in the cap. And I am resizing it and I am applying the MiDaS or the depth estimation. So it's same as the above code. And so I'm normalizing it and everything is being done here. So see, we are getting a depth map of an numpy array. So, and I am calculating, I am implementing YOLO object detection. So it's same as the above course. And from here, we are applying the tracker. So you can see here. So I have initialized the tracker in the above cell of the code. And from here, so I am keeping the track of the object which is going in front of us or in front of our vehicle with the help of the directions of np equal to np dot array of directions. So At last, I'm doing a fusion or the fusion of all the three MiDaS, YOLO, and the tracker. So especially by tracker. So it's an same parameters which we have used in the depth. So it's an inverse because we have know that we need to calculate the inverse of the depth to get the actual distance of our vehicle and the vehicle which is going our print, right? So in the final one, I am printing just how many frames I am pre-processed and everything, and at last I am releasing everything. So with this, the module one is completed, and the module one workflow, which is nothing but I have shown already. Um, it is a module one workflow, so we are been taking the compressor input and decoding and we are converting into the raw frames PRA RBG. And for the YOLO detection, we will be taking that same RBG and we will be getting the output. And for the MIDAS, we will be converting into the BRG into the RGB because OpenCV retrieves BRG as a default. And so we will be implementing the tracker and we would be doing the fusion of all this YOLO, MIDAS, and the tracking. At last, we would be getting a output video with the help of the stacking of the images. So I will be showing that module one final video. It's a module one final video. You can see the ID. So the IDs are 979, 986 because I have run the multiple times to debugging my model. So because of that, the IDs are being increased, but the IDs are unique, right? So it's the output of the video. You can see that each and every ID is unique and the object is being tracked successfully. So with here, the module one is being completed. Now we are going to the module two, the planning software. The module two, so here I have installed each and every dependencies and everything which I would be needing to implement the module two, which is nothing but the planning module. And I have imported the dependencies, OS and everything, CV2, YOLO, and everything. So I am setting up my CUDA for the parallel execution, and I have loaded my YOLO model as well as a MIDAS model, and I have initialized the tracker. So I am using a byte tracker. You can use your one type of the tracker. For example, you can use DeepSORT or any other type of the tracker. But the by track is basically easy to use. So I am using this. And in the module one, I have compared both the codes, the DeepSORT as well as the by tracker. And in the fourth, I have been loading the SageFormer segmentation model. So the seg processor is nothing but it makes the frame or that particular image ready to process for the seg model. Seg model is basically a pre-trained neural network which is being used to find the segmentation on the road with the help of the masking. And I have denoted the input video path and the output video path. As you can see here, I have initialized the CUDA and I have loaded model successfully and I successfully initialized the byte tracker and everything is going well. And here I have defined a grid for the scaling and to get a good segmentation and to get a good view from the mirror which we are driving. So you can use the region of interest as you wish. And I have taking the run RBG, NP array, and so I'm checking whether it's open or not, and I am calculating the FPS and everything. So to get the same FPS and the same properties output video, and I would be using the codec for the decompression of the input frames, which we are been converting into the output frames for the compressing of the output frames and the stacking into the MP4. So I would be using the codec and everything. It's the same as the module one code. So for the just for the understanding purpose, I have written twice. So with code with this single section code, also you can be implementing the module one plus half of the module two with up to the SageFormer segmentation, and this is the module one perception. So I am inserting the MiDaS, YOLO, and the byte and so from here the module 2 would be the starting. So in the upper cell I have initialized the SageFormer, right? So here I'm applying a mask for to extract the segmentation area on the road, and also I have initialized the tracker which I am using here to track the object. So it shouldn't be able to extract or the mark green color on the objects which are going on the road or which are going on that particular area of road, right? So I am with this logic, I am removing that semantic segmentation on the vehicles which are going in the road, as well as the area below the vehicles and everything. And also, I am detecting it with the help of the logic one equal to obstacle and the zero equal to desirable. So it would be getting the output in the terminal. Like if 0, you can move on that particular section of the segmented area, or if 1, you need to be get stopping. And these two are being used in the module 3, and so I have installed the tracker. So it's same as the above, but some change in the logic, and having scheduled the start node and the end node for the references purposes. And for the visualization, I have combined the both modules. So I am drawing the drivable area as a green after the segmentation after applying the mask, and also the tracker objects are being recognized with the color of the blue. So you can assume that it's an YOLO. So we are performing YOLO here with the help of the blue color and the class names and the class IDs. And the class names are nothing but class, truck, bus, cyclist, etc. So in my case, there are more cars, and there is, I think, very less number of trucks and buses. I think no cycles have been found in that video. So the majority would be like cars. And I am getting the depth MiDaS and creating the labels and the drawing boxes for the visualization purposes, and printing the type of the label that they have. And I have combined the S-star algorithm in this cell itself. So you can see here, I have combined the S-star algorithm. So this path is being used in the next cell for the S-star algorithm. And so I'm releasing everything, and so from here the module 1 plus 2 would be the completed. So the HTML algorithm I have implemented separately, and with this the path I am calling that. So I would be showing that HTML algorithm. So you can see that the input, I mean the output video is being saved. So I would be showing the architecture as well as the output video of this semantic segmentation. So this is the architecture. The for the input video frame is been decompressed and taken into the NumPy RBG, and then SageFormer processor. And then with the help of the neural networks, we would be applying the mask to extract segmentation, and we would be using a star for the shortest distance. And we would be using the cost map, whether to know that free to go or we need to be stop or one to block, and we would be finding the best path with the help of the STAR algorithm. And after that, we are combining every semantic segmentation plus this cost map for the purposes of drivable or not drivable. So now we are going to the A-star algorithm. So it's the A-star algorithm. So I have downloaded the dependencies and everything. So I have imported the dependencies, and the same as I have defined the grid and the region of interest. Because I need to be ignoring dashboards and the side mirrors as well as the rear view mirror, right? For getting the clear view of the road. So you can change the cutoff as well as your input video as your data, and it's same. I am decompressing it and taking a run on PRBG and initializing the tracker and saving into the A-star path, and taking each and every frame and resizing the frame and implementing the module 1 with the YOLO and MiDaS. And you can see here it's a formula for the region region of interest, and you need to change the X1 X2 as denoted above as you need for your data. And so you can see that. So I have implemented everything module 2. So and I have implemented the start node and the end node with the STL algorithm, and it's for the visualization purposes with the tracker and everything. So to see the final output video, I will be downloading in the next code of section, and I have implemented the map and the STL algorithm, and I have released everything. So I would be showing you the output video of this module 2. So this is the final output video of the module 2. You can see that module 1. So we are having the YOLO plus ID plus the distance between our vehicle to the moving vehicles on the road, and also the segmented area on the road with the green color. So it's an output for the second module and the first module, both are combined. So it's a module 2 planning, and this module 2 output is being sent into the module 3. Now we are going to the module 3. Module 3 is about the control. So first I am downloading the each and every dependencies I should be needing. And the module 3 is basically nothing but it should be telling the steering speed and the acceleration. We need to be going front or back with the simple conditions. So basically it's the easiest module compared to the all three modules. And I would be importing everything, and I would be setting up my CUDA for the parallel execution. And I am loading my YOLO model as well as the MiDaS, and I am initializing the by track. It's your wish to initialize the and the tracker for the DeepSORT and everything. It's your wish, but by track is the easiest track. We can easily track with the less number of resources and everything. So I have imported the Sage Pharma segmentation model, neural network applying mask and preparing the cost map, everything, and also I have defined the path. So I have defined the path, and so here it's an extra of pathfinding algorithm which I have implemented in the module 2. You can also again implement it. So it is just for the helper functions, just for the understanding purposes. I have written these functions again. So it's and so from here the behavioral logic becomes and for calculating which lane we are passing and which line we should be driving for the model to know whether the if we are crossing the different lanes, can we go or can't we go? Is there any vehicles crossing the lanes and everything is being behavioral logic functions is being everything is seen or updated by this particular logic. And we are seeing that in that tracks what are the different types of the objects and you need to be setting the particular pixel value of your vehicle. So based on that pixel values and based on that pixel values of the opposite vehicles would be calculating whether it's safe or not. So this logic I have written for the obstacle detectance. So you can see here it's in thresholds. So if the threshold exceeds, it would be repeating or it would be displaying its respective outputs as well as the how much target speed we would be going and how much speed can we go in that line. Everything is being done in this logic and it's same I have defined that region of interest and everything. So based on my data and I have denoted the steering PIDs and the speed PIDs to for the simulation of the speed and the how much speed the vehicle is going and everything. So at last, I'm opening my I'm video and converting into the RAW, then again codec, and from module 1 to module 4, I'm implementing everything to get a clear idea. And this is the module 1. So and up to here it's in module 1, so it's in module 2 planning. So just I'm importing that I'm using here for the installation purposes and for knowing the steering angle, how much the angle of the steer should be there to reach the desired star path. So with this logic I'm finding this and I am generating an goal node, so to overtake a vehicle in between you or in front of you, so it would be becoming a goal node and after you are crossing that goal node, so other vehicle which is before you would becomes a goal node. So it's an basically an iterative, I mean recursive process and the path. So the at last I am initializing and calling everything in the module 3 from the steering angle to the speed and everything. So displaying my current speed, steer angle and everything start or stop for the visualization purposes. So it's just for the visualization code like put text. So for the visualization to keep and that text in that particular frame or in that particular video I am keeping this text like the state target, how much target speed should we need and the steering angle should we need and everything is been putting there and I am counting the number of frames. So for displaying the number of frames are being processed. So by default the gap has been 50 processors and at last I'm saving and downloading the final video into my OS environment and in my OS. So it's the project. So at last we have implemented the module 1, module 2, module 3 and combined all three modules. So to get an final output video. So I would be displaying my final output video. This is the final output video of the module 1, module 2, module 3. You can see here. So it's a car with an ID and with YOLO and with the each and every uh, stop, steering speed and everything. So you can see here the state is being stopped and he is going. So you can see the change in the speed and the drive. So it's the final output of the video with the module 1, module 2, module 3, all the combination. So so you can see here the changing of the parameters in the frames. So basically it's starting is stop due to the vehicles which are going below and now the speed is being changing and it's went to the drive right. So it's the final output video of the project. Thank you.